Hello students, welcome to IMS GATE Academy. So, and welcome to GATE Booster session for manufacturing session 2. Okay, hope you enjoyed the last session yesterday related to the casting and welding processes questions. Now we just shift our talk onto some other manufacturing questions. Today I am going to cover metal forming processes as well as metal cutting process. I am going to cover for a beautiful questions. Okay, now let us go for the session. Now myself, I am Vijay Kumar. So finished my PhD and pursued MTech in NIT Surathkal, and I have a teaching experience of 10 years in manufacturing for GATE aspirants. Okay. Now have a look on the question. First question that is yeah. So first question. So a metal strip, let me read the question. A metal strip is rolled from an initial thickness of, so initial thickness is, this is your initial thickness. So initial thickness of 3.5 mm and final thickness is 2.5 mm. So in a rolling operation, a workpiece is compressed or rolled in between two rollers and from initial thickness of 3.5 mm to final thickness of 2.5 mm in a single pass rolling operation. So in a single pass rolling operation. Yes guys, next with a roller diameter, so roller diameter is given, the width of the strip is 450 mm and the average coefficient of friction between the strip and roller is 0.08. Consider the flow stress of material is 140 megapascal, and if the entry velocity of the strip is 55 mm per second, roller rotates at a speed of 5 rpm. Determine the maximum pressure induced in the rolling operation. Clear everybody? So here they gave that initial thickness and final thickness, and roller diameter is given, coefficient of friction is given, workpiece width also given, and then so average yield stress also given. Now we have to find that maximum pressure which is induced in the rolling operation we have to find. Okay guys, now let us go to solve this problem. Okay, initial thickness given data. From the problem you write given data first. Given data, initial thickness is H initial is equal to, it is 3.5 mm and final thickness HF is equal to, it is 2.5 mm. All right, right. Next is single pass rolling operation, roller diameter D is equal to, it is 250 mm. Roller diameter is 250 mm and width of the strip is, that is B is equal to, it is 450 mm. Yes, yeah, width of the strip is 450 mm and coefficient of friction between the roller and workpiece is 0.08. So coefficient of friction mu is equal to, it is 0.08. Next, what is given? Entry velocity. So flow stress is given. Now flow stress of workpiece material is equal to, it is 140 megapascal. Yes guys, so I'm just writing the given data. Okay, right. Now next is entry velocity. Entry velocity of the rolling V0 is equal to 55 mm per second is given. 55 mm per second is given. Okay, next is what is given? Roller RPM. Speed of the roller is given, that is equal to, it is 5 RPM. This is what given. What we have to find guys? Maximum pressure induced in the rolling operation we are supposed to find. Say that maximum pressure P max we are supposed to find. Yes guys. Okay. Now, as we know that maximum pressure induced in the rolling operation is at neutral point. Okay, at neutral point maximum pressure is going to be produced, okay, or generated. Okay, now let us go for, so P max. How can we write P max? So P, oh my god, 1 minute. Maximum pressure in rolling either in the lagging zone or leading zone, that is equal to sigma y is divided by n into, it is n minus 1 into, it is gonna be a h initial, that is h initial or h naught is divided by hn whole power n plus 1 will be your maximum pressure. Okay, now we know that h initial, just now we had seen na, h initial 3.5 is given, but we don't know hn, and n we have to find, sigma y also given in the problem. Yes guys, okay, now accordingly we just find that. In the rolling operation, so this will be your roller, and this is a one more roller, and somewhere here. Now my workpiece will be like this. My workpiece will be like this. Okay. Now as we know that this is our deformation zone. This is our deformation zone. Okay. Now let me highlight that deformation zone. Now see this is our deformation zone. Okay. So I'll write deformation zone. This is our deformation zone. Now this we know that it is a H initial and here it is a H final. As we know that somewhere in between the H initial and H final, we may find that, you know, Hn. That means so Hn is a thickness at neutral point. Thickness at neutral point. Okay. Now this roller is rotating with certain velocity. Say that v. So this roller is rotating certain velocity v. Okay. Now in the problem they gave that, see guys, initial velocity of the workpiece, that means see that, so velocity of the strip in rolling rotates. Okay, right, that means see initial velocity, roller workpiece, this is a workpiece guys. So initial velocity before entering into the rolling stand, what is the velocity of the workpiece? That is v naught equal to 55 mm per second is given, isn't it guys? Okay, this is given. Right, now we have to find Hn. If you know the Hn, so that it is very easy to solve the is very easy to find out the maximum pressure induced in the rolling operation. As we know that you know, rolling pressure maximum at the neutral point. Whenever roller is contact with the neutral point, at this neutral point the maximum pressure is going to be induced. So in the beginning of rolling, the rolling pressure is 0. As the rolling progresses, the pressure is going to be increased and it reaches to maximum at the neutral plane, and beyond the neutral plane the pressure again decreases and reaches to minimum. But entry pressure, exit pressure are different. Okay, entry pressure is 0 and exit pressure is more. Okay, when compared to entry and exit pressure is more than the entry pressure. Clear everybody guys? Okay, right. Yeah, now here let me go for Hn. Hn. So how to calculate Hn? So in rolling operation we know that whatever the volume flow rate entering into the rolling stand, same is going to be existed. That means volume flow rate in rolling operation is going to be constant. Suppose say that I can write it is, you know, volume flow rate in rolling operation is constant. So that volume flow rate before rolling is equal to volume flow rate after rolling. Okay, now let me write that statement. Volume flow rate before rolling is equal to volume flow rate after rolling. Volume flow rate after rolling. Volume flow rate after rolling. All right, guys. Volume flow rate after rolling operation. Okay, right. Now, Bhushan, it is not 185. Check your answer once. Okay, right. Now, now what is volume flow rate? How can we write volume flow rate? Okay. Now, I just go to the previous. So, V initial, and then here also the velocity of the workpiece after rolling is Vf. Okay. Now, Hi V naught into B naught is equal to, here suppose if I draw the width of the workpiece, it would be like this. Width of the workpiece, it would be like this. Right. Now, this will be your width B, and here it is, suppose say that it is a B initial and it is B final Bf. Okay, right. Now, let me write that volume flow rate, that is equal to H initial into B initial into V naught is equal to, H final into B final into V final. Yes, guys. Okay. So, from there, so actually we can plot the volume flow rate like this. That means where we have plotted volume flow rate in between H initial and H final. H initial and H final. Okay. Now, this is a velocity of the workpiece before it is going to enter into the rolling operation. Now, it is a velocity after rolling operation, the workpiece of the velocity of the workpiece after rolling operation. Right. Now, in between, in the deformation zone, the velocity of the workpiece is continuously changed, as we have discussed, isn't it? Now, here what happened? The workpiece velocity at neutral point is equal to roller surface velocity. I said that in the beginning of rolling, workpiece velocity is very less. As the rolling progresses, velocity of the workpiece is continuously increases. Somewhere at neutral point exactly, the velocity of the workpiece is equal to velocity of the roller. Okay. So, roller surface velocity is equal to now workpiece velocity at neutral plane. Now, I am going to plot the same volume flow rate in between these two. So, volume flow rate in the deformation zone is constant, na? That is why volume flow rate in the beginning, volume flow rate at the neutral point, both are same, na? So, that is why I will plot the, from this I can write from above, okay. So, H initial into B initial into V naught is equal to, Hn into Bn into, V. Why? Because roller surface velocity at neutral point is equal to workpiece velocity. Clear, everybody? Okay. Hope you understand. Right. Now, from here, as we know that it is B initial is equal to Bn. Why? Because in the rolling operation, width of the workpiece we consider it as constant. That is why width of the workpiece is constant. Now, here H initial into V naught is equal to Hn into V. Yes, guys. Now, we don't know V. So, roller surface velocity we don't know. So, how to find this? If I able to find this, we know this value and we know initial velocity, so that Hn also we can easily find out the Hn if you know the V. Okay. Now, let me calculate that roller surface velocity. Roller velocity is equal to, it is pi d n by 60. Pi d n by 60. Now, what is the diameter of the roller? And RPM also given, na? So, RPM also given, right? RPM of the roller is given, diameter of the roller also given, right? From there we can calculate that. So, what is the roller diameter? It is 250, right? Now, here I can write it is pi into 250 into 5 RPM is divided by 60. So, that I will get my roller velocity V is equal to, it is 65 mm per second. 65 mm per second. Okay. Now, go back to our relation. What is our relation? H initial into V naught is equal to Hn into V. Okay. Now, I require Hn, na? Hn is equal to, I can write it is H initial into V naught is divided by V. Okay, what is H initial? H initial is 3.5 and V naught is how much V naught, guys? V naught is 55 and this is 65, such that I am going to get my Hn value, 2.96 mm you will get. 2.96 mm you will get. All right, guys. So, like that we can calculate your Hn. Once you know the Hn value, if I substitute my Hn value here, so I know that sigma y, n I have to calculate, I will calculate n. Now, let us go for calculating the maximum pressure. Okay. Now, P maximum is equal to, it is sigma y, that is flow stress by n into, it is n minus 1 into, H naught or H initial is divided by Hn whole power n plus 1, isn't it? So, what is n? N here is n equal to, it is 2 mu L by delta H. 2 mu L by delta H. So, what is delta H? Delta H is equal to here H initial minus H final. So, H initial we know that is 2.5 minus H final is equal to 2.5, such that we are going to get it is 1 mm. Okay. Now, what is L? Length of deformation zone. So, that is equal to R into delta H. Okay. Now, what is R? R is 125 na, radius of the roller, and delta H is 1, such that you are going to get L equal to, so 125 root we will keep, so if I keep all this in this, you will get n. So, now n equal to, it is 2 into mu 0.08 into L is 125 into 1 under root is divided by 1, such that I am going to get my n value is equal to 1.79. 1.79 my n value I am going to get. Clear, everybody? Okay, guys. Okay. Now, let us go for substituting all the values. So, now P max. So, here it is sigma y is how much, guys? Sigma y? Sigma y is 140 and oh my god, 1 minute. Now, sigma y is 140 is divided by n is 1.79 into, it is 1.79 minus 1 into, it is H naught. H naught is 3.5 is divided by 2.96 whole power 1.79 plus 1. If you solve this, you are going to get your P maximum pressure in the rolling operation is equal to 161.16 megapascal. Okay. So, if you solve that, you are going to get your maximum pressure in the rolling operation is, P maximum. Okay. Here all about in this question, you are supposed to find out your Hn value. That means thickness at the neutral plane. Okay. So, thickness at the neutral plane, if you are able to find out this thickness of neutral plane, so that it will be very easy to solve this kind of question. So, as we know that at neutral point, maximum pressure induced in the rolling operation. Clear, everybody? Hope you understand. Okay. Yeah. So, now let us go for next question. Yeah. Have a look on this question. It is related to wire drawing. Yeah. Read the question once, guys. Then we will solve. Yeah, Bhushan, you can consider leading zone formula also. Okay. So, because at neutral point, lagging zone pressure equal to leading zone pressure, that is equal to maximum pressure. Okay. You can consider, not an issue. Yeah. Yeah, at neutral point, lagging zone pressure equal to leading zone pressure, and that is equal to maximum. Okay, anyone you can consider, but you have to keep that Hn value. So, if you go for that, you will come to know. Let us go back. See, here formula will going to be changed. Okay, Hn by Hf will come. Okay, so I will also write that formula. So this is for lagging zone Bhushan. This is for lagging zone. For leading zone P maximum. For leading zone P maximum sigma y by n. So into it is n plus 1 into it is hn by hf by hf whole power n. So minus 1. So if you use this formula also, you will get the same thing. Okay, right. So hope you understand. Now let us go back to the question. So have a look on this question, guys. Wire drawing operation. A wire of 5 mm diameter is drawn into wire 4 mm diameter through a conical die at a constant pulling speed of 5 meters per second. Okay. So wire initial diameter 5 mm is drawn into 4 mm. So 5 mm wire is going to be reduced to 4 mm, guys. Okay. Now the drawing speed is given. Neglecting the coefficient of friction and redundant work, the drawing stress sigma d in megapascal for the above process given by this is. So they only gave that drawing stress formula. This is what drawing stress formula. They considered that neglecting the friction. That means mu equal to 0. Now where sigma bar is the mean flow stress of wire in material of megapascal and is ratio. So and R, see this, guys, and R is the ratio of decreasing in area of cross section to initial cross section of the wire. So read carefully, guys, read the statements carefully. What is the gave that? R is the ratio of decreasing in cross section to the initial cross section of the wire. Decreasing in cross section and initial cross section area of the wire. If the mean flow stress of wire material is 600 megapascal, okay, sigma bar is also given 600 megapascal, then power required in kilowatt in the above wire drawing operation. Okay, so we have to find the power required for drawing operation. Here what happened now? So a wire is there which is having the 5 mm diameter, it is going to be reduced to 4 mm. So during this operation 5 meter per second speed is used for drawing operation, and drawing stress, the formula is given, and it is a mean flow stress that is mentioned in the problem, and or they define that it is a ratio of decreasing in cross section area to the initial cross section area. Okay. So if you find that, if you find R value and substituting here, so that you will get drawing stress. All right. So once you get the drawing stress, drawing force can be calculated. So drawing force into velocity, so that you will get power. Okay. So what we have to find, guys? Power required for the drawing operation. Power required in kilowatts for the drawing operation we have to find. Okay. So I just draw the simple diagram for to understand this. So this is what our wire. Right. Now initial diameter is 5 mm. Okay. Initial diameter is 5 mm and final diameter is 4 mm. Yes, guys. Initial diameter is 5 mm. Final diameter is 4 mm. So what is the drawing speed, guys? Drawing speed is equal to 5 meters per second. Isn't it? 5 meters per second. Now what we have to find? So power required for this drawing operation. How can we calculate power? Power equal to drawing force into drawing velocity, so that you are going to get power. Now we have to find the force required for the drawing operation. Force required for the drawing operation, and if it is multiplied with the velocity of the drawing operation, so that you will get the power. Isn't it, guys? So for that, yeah, very good. No. So Bhushan, once you check your answer, it is not correct actually. Okay. Yeah. Anyway, let me solve myself. Okay. Right. Now here, so force we have to calculate. So how can we find out the force? Force is equal to stress into area, right? Drawing stress into drawing area, so that you are going to get force. So force into velocity. First, let us calculate that drawing stress. Okay, drawing stress formula given in the problem now. Now let us go for how to calculate stress. Okay, drawing stress. Stress required for drawing is equal to, it is sigma bar into, it is what is given? ln of 1 by 1 minus r. 1 minute. Ln of. Now let me write this. Right. Now sigma bar is the ln of, it is 1 by 1 minus r. This is what the drawing stress. Okay. Now sigma bar is given. What is sigma bar? So they said sigma bar in the problem, guys. What is sigma bar? Sigma bar is the mean flow stress of wire material, and they gave that the mean flow stress of wire material is 600 megapascal. Right. Now here sigma bar is a 600 megapascal. Okay. Now we have to find R. What is R? What is R? So now let us go back to our question. What is R? The ratio of decreasing in cross section area to the initial cross section area. Okay, right. Now suppose my cross section area, initial cross section area A0 I will consider, and final cross section area AF I will consider. Okay, what they said, R is equal to ratio of decreasing in cross section area. Decreasing cross section area means A0 minus AF is the decreasing in cross section area, isn't it? To that initial cross section area, the ratio of decreasing in cross section area to the initial cross section area. So that can I write my R equal to, it is decreasing in cross section area A0 minus AF is divided by A0, isn't it? Decreasing in cross section area to the initial cross section area. So that I will get my R, isn't it? Now from here I can write my fellow, it is, so 1 minus, it is AF by A0 I am going to get. Yes, guys. Now what is A0 and AF? How can we calculate? So A0 equal to, it is pi by 4 D0 square, and AF is equal to pi by 4 DF square. Okay. So what is D0 and DF? What is D0 and DF? This is my D0 and this is my DF. Okay. So initial diameter D0 and final diameter, initial cross section area of the wire and final cross section area of the wire. Clear, everybody? Right. Now let us go for substitute this value here. Okay, I can write directly here R equal to 1 minus, so pi by 4 DF square is divided by pi by 4 D0 square, isn't it? Right. So from there, so it's just take it as a box. Okay, right. From there, R equal to, I can write it as 1 minus DF square is divided by D0 square. So from here, I can write it as 1 minus DF is 4 by 5 whole square, such that I am going to get my R value is equal to, it is 0.36 I am going to get. 0.36 I am going to get my R value. I know that sigma bar R, and so that I can get sigma D na. Now right now let us write sigma D, that is equal to 600 ln of 1 by 1 minus 0.36, such that you are going to get your drawing stress, you are going to get, it is 267.77 megapascal you are going to get as a drawing stress, isn't it, guys? Okay, yeah. Abhijit Habenerji, okay, it is 16.82 kilowatts is the correct answer. Very good, very good, very good, guys, very good, excellent. Yeah, Bhushan, check your answer once. Okay, yeah, good evening, sir. Good evening, Atul, sir. Right. Now we have found that drawing stress. Now what is the drawing force? We have to calculate. Power equal to force into drawing velocity, na? That is the reason why here we have to calculate the drawing force. Okay, now let us go for next slide. Drawing force is equal to, I'll change the ink. Drawing force is equal to drawing stress into final cross section area. Okay, so you may ask that, sir, why can't we consider that initial cross section area? Why? Because during the drawing operation, so these are the dies. So these are the dies. Now we are applying the tensile load in the drawing. So from here we are pulling the rod from here in between the two stationary dies. That is why we are applying load here, load at the end. That is why this cross section area we have to consider, drawing stress into this cross section area so that you will get drawing force. Okay, so we are applying tensile force in the drawing operation. That is the reason why here we have to consider final cross section area on which you are applying the tensile force. That area you have to consider, right guys? Okay, now from there I can write, so drawing stress, just now I got that, how much it is, 267.77 into pi by 4 into df square. So what is df? 267.77 into pi by 4 into df square is a final square, 4 na? Yeah, 4 square. From there, drawing force I am going to get, it is 3364.897 newtons I am going to get. Okay, so up to here clear. Right, now here next is no Bhushan, it is not 269, it will come around 16.82 kilowatts will come. Okay, right, now drawing force, drawing power is equal to P is equal to drawing force or drawing load, drawing force into what is that? Velocity, drawing velocity. That is drawing force is equal to 33.64.897 newtons into, it is, what is the velocity guys? What is the velocity given? Drawing velocity 5 meters per second, 5 meters per second. 5 meters per second. Okay, so it is meters per second. Now it is in newtons. Newton meter is a joule na, joule per second. So that watts you will get in watts. That is how many watts you will get? 16824.485 watts you will get. Okay, watts you will get. Why? Because Newton meter is a joule. Joule per second is a watt. Okay, Bhushan, got it? Very good, excellent approach, Bhushan. Thank you. Now here they ask in the problem, that you have to find your power in terms of kilowatts, right? Now for that kilowatts, divided by 1000, so that you are going to get it is 16.82 kilowatt. 16.82 kilowatt. Like that you are supposed to solve the problem. Clear everybody? Understood? Hope you understand. Okay, Bhushan, where you have done mistake, correct your mistake. Okay, so by following the lecture. Clear everybody? Right, now here see guys, so whenever they give these kind of question, okay, by seeing that formula, don't get confusion. Okay, don't get confusion. So just read the problem statements properly so that it will be very easy to solve the question. Okay, actually this is a very easy to solve. Actually they said that it is A naught minus AF by A naught, isn't it? So now here if you solve this, so sigma y into ln of, you will get it is A naught by AF. A naught by AF. Okay, yeah, good, very good Bhushan, very good. Yeah, R is not subtract from 1. Okay, no problem. Okay, so then only you will get. So hope you understand the question. Okay, thank you all. So for this question, now let us go for the next question. Hope you understand all this. Yeah, have a look on this question. It is related to extrusion. Right, so read the question carefully. I'll be back in a minute. Yeah, thank you Balaji, thank you very much. Okay, right, now let me read the question. Right, a cylindrical billet of diameter 100 mm and 100 mm length is extruded by direct extrusion process. What is that? A 100 mm diameter of the workpiece, and also it is having 100 mm length, and it is extruded by direct extrusion process. Okay, right. So direct extrusion process to produce a bar of L section. So through this extrusion process, they are producing the L section component. So this process is direct extrusion process. Through this direct extrusion process, they are going to produce L section bar. L section, the cross sectional dimensions of the L section bar is shown in the figure. So this is what the component produced by the extrusion process. Okay, by taking the workpiece of 100 mm diameter and 100 mm length. Okay, right. Now above process. So next, the total extrusion pressure in megapascal for the above process related to extrusion ratio are as P equal to this much. Okay, so extrusion pressure also given in this problem. Okay, now where sigma m, this is sigma m. Sigma m is the mean flow strength of the billet material. Billet material means here workpiece material. Okay, next megapascal, and L, it is L, not 1 guys, it is L. L is the portion of the billet length remained to be extruded in mm. That means, so before extrusion process, what is the length? That is called L. Okay, now the portion of the billet length remaining to be extruded in mm. Now where D0 is the initial diameter of the billet. So now D0 is the initial diameter of the billet. Next, what is given? And Ks is the die shape factor. Ks is the die shape factor. Ks is the die shape factor, isn't it? Now shape factor is 1.05. Ks is given 1.05. Then maximum force required at the start of extrusion is. Okay. Now if we have an idea about the direct extrusion process, so that it will be very easy to solve this kind of question. Okay. So let me solve this question with the help of the diagram. Clear everybody guys? Okay. Now I'll write the given data, and then the data I'll present in the diagram, so that we will be able to find out the force required for the extrusion process. Clear everybody? Okay, right. Now let us go further. What is given? So direct extrusion process, I'll just draw a brief diagram. This is what your L section is going to be produced. Now here this will be your ram. This will be your ram. This is what the direct extrusion process. Okay. Now see, this is your billet. Okay, billet. This is your billet. Now, so what is the initial length of the billet? Length of the billet L0 is equal to 100 mm is given na? 100 mm is given na? Right. Now see that initial length of the billet is 100 mm. Now diameter of the billet. So now diameter of the billet, this diameter. So this diameter of the billet is 100 mm. That is D0 equal to 100 mm. 100 mm. Right. So if I operate my ram, this is ram. If I operate ram, and this is my billet. Okay. Now this is your extruded L-shaped component. Extruded L-shaped component. L-shaped component. L-shaped component. Now, so if I apply force from the ram onto the billet, then this billet will take L-shaped section shown in the figure. Okay. So this kind of object is going to be produced. This is called direct extrusion process. Direct extrusion process means, so the ram direction and extruded component direction both are in same. So it is a round billet. So here I have drawn that it is a 2D diagram, but assume that it is a cylindrical billet which is diameter is 100 mm and length is 100 mm also. Diameter is also 100 mm and length is also 100 mm. Now what happened now? Now, whenever you operate this RAM, then what happen na? This die shape is L shape, such that L shape component is going to be produced. Okay. Now, for this operation, yeah, thank you, Prasanna, thank you very much. Yeah, thank you, Shantakumar. Bhushan, 741. Let me check. It is no, Bhushan. Force required for, let me solve. You check your answer with my solution. Okay. This is what happening. Now, what they are asking now, what force required for producing this billet to L-shaped component? The force is they have to calculate. Now, they gave that pressure equation they gave. So, pressure into cross-section area, so that you are going to get force na. Pressure into cross-section area is going to get cross-section force of the extrusion. Now let us write that pressure equation. Okay. Now, let me write that pressure equation, right. So, pressure multiply with the cross-section area, so that you are going to get, what is that? Force, extrusion force. Now let me write pressure equation. P is equal to, it is Ks into sigma m into, and it is 0.8 plus 1.5 into ln of extrusion ratio, and plus 2L by D naught, plus 2L by D naught. Yes, guys, 2L by D naught. This is what the pressure they gave. Here we have to find, Bhushan, it is 2429 kilonewtons will come, Bhushan. Okay. Yeah. Thank you, Chandrakumar. Thank you very much. Okay, right. Now, here we need to, as we know that sigma m is given in the problem, right. Now, let me write that given data. Sigma m is how much, guys? Sigma m is the mean flow stress of material given somewhere. Mean flow stress of billet material is megapascal, and here 50 megapascal is given. Okay. Now, so sigma m, Ks is also given. What is Ks? Ks safe factor is 1.05, right. Now, let me write that sigma m is 50 megapascal, and Ks is a safe factor, die safe factor is 1.05. Now, or we have to find L. What they define L? It is D naught, guys. It is D naught. Okay. So, I just erase this and write it again. It is D naught. Okay. Now, D naught. What is L? They gave that, guys. L. How can they define in the problem? L. So, where L is the portion of the billet length remaining to be extruded. Okay. So, now portion of the billet remain to be extruded, so that L naught equal to L. This is what L na, right. Now, here L equal to 100. L equal to 100 and D naught equal to also 100. Now, here we have to find R. What they said that R equal to extrusion ratio. Okay. Now, this is quite important in calculating the extrusion ratio, right. How can I write extrusion ratio? Extrusion ratio is equal to initial cross section area divided by final cross section area. Okay. What is initial cross section area? Right. Billet cross section area is the initial cross section area. Now, what is the shape is going to be produced through the extrusion process, that is come under final cross section area. So, what is the component is produced? What is the component is produced here? L-shaped component. This cross section area is the final cross section area, right. Now, this billet cross section area is the initial cross section area. Now, what is the billet cross section area? It is a cylindrical shape, na. That is why pi by 4 d naught square is the initial cross section area. Yes, guys. Okay. Yeah. Now, let us go for, right, initial cross section area. A naught is equal to, it is pi by 4 d naught square. Okay. Now, pi by 4 into 100 square, such that A naught you are going to get, it is 7853.98. 7853.98 mm square you will get. Okay. Now, let us calculate that A final component cross section area. Component cross section area, this cross section area. So, this distance, let me change my ink. So here divide this section into two parts. This is section 1 and section 2. Now 10 by 60. 10 by 60. Now it is 50. Already 10 is gone now. So that is 40 into 10. 40 into 10 and 10 into 60. Okay. Now here my cross section area of final component is, it is 60 by 10 plus 40 by 10. Okay. Right. Now here it is 600 plus 400. So that I am going to get my 1000 mm square my cross section area. Right. Now let's calculate that R. R equal to here AF 7853.98 is divided by 1000. Yes, guys. From there I can write it is 7.85 is my R. Yes, understood. Please do respond, guys. Okay. So hope you understand. AF initial cross section area of the billet. Billet is initially it is 741. Initial billet is cylindrical shape. That is why its cross section area is pi by 4 d square. Now final cross section area of the component, L shaped component cross section area. How can we calculate L shaped component cross section area? This cross section area plus this cross section area. This cross section area is 10 by 60 plus, so here it is 50. Already 10 is inserted in this block now. That is the reason why here 40 into 10. So 400 plus 600, so that you are going to get it is a you are going to get it is a 1000 mm. Okay. Now we got all the terminology which are present in the formula. So now we got that Ks, sigma m 0.8 we got, this standard values, R value also 7.85, L is the 100, D naught is also 100. So that, thank you Chandramouli, thank you very much. Right. Now here we are going to get here, we just substitute the values so that we will get pressure. Okay. Now let us go for substituting the values. That is P is equal to, it is Ks 1.05 into sigma m is a 50. And it is gonna be a 0.8 na? Yeah, 0.8 plus 1.5 into ln of R. 7.85 is a R. Okay, this is plus 2L. 2L is 100 and D naught is also 100. So now 100 will get cancelled. If you solve this equation, if you calculate that, you will get pressure is 30.1 minute. You are going to get your pressure is 309.26 megapascal. You are going to get. Yes, guys, 30.96. Thank you very much. Thank you, Sampath. Okay, right. Now pressure we got. But they didn't ask the pressure in the problem. They ask you what they ask you in the problem, guys. What they ask you problem? So pressure, not pressure, force required, maximum force required for the operation. So that how can we get the pressure? Pressure will get pressure multiply with the area, so that you will get the force. All right. Now let us go for that. Right. So force for extrusion. Force for extrusion. Okay, that is equal to pressure into cross section area. Cross section area. Yes, guys. Pressure into cross section area. Now the question is, which cross section area we supposed to consider? Okay, in the drawing operation, the wire is drawn like this. That is why we are applying the final area of the drawing, isn't it, guys? Okay. Now here in extrusion process, which area we are supposed to consider? Which area? Either final cross section area or initial cross section area. Which area we are supposed to consider? Okay. Why? Because see, in extrusion process we are applying the force from the back side. Now that is the reason why here initial cross section area has to be multiplied with the pressure, so that you will get the force required for the extrusion process. Okay, that is the difference between the drawing and extrusion process, guys. Okay, are you getting my point? So in drawing operation, why we are considering it as the final cross section area? In extrusion process, why we are considering the initial cross section area? Is the difference is that in drawing operation we applied the stress or load at the front side of the drawing. In extrusion process we are applying the pressure at the back side of the workpiece. That is the reason why initial cross section area has to be considered. Hope you understand all. Okay, initial area more than force required, also more hence initial. Okay, so no, and what area you are applying the pressure, that area you have to consider Bhushan. Okay, that is why here initial cross section area is, what is initial cross section area here? A naught is equal to pi by 4 d naught square is the initial cross section area. Okay, right. Now let us go for, so from where we are applying the pressure, so on the billet we are applying, not on the component. But in wire drawing operation, on the component we are applying front side. That is why final cross section area has to be considered. Okay, right. Now let us go for calculating this. Now pressure, I got that, here it is 309.26 megapascal into pi by 4 d naught square. Okay, again I'll write it is 309.26 into pi by 4 into 100 square. Okay, now if you solve this, you are going to get your force is equal to, you know, it is 2429.78 kilonewtons you will get. 78 kilonewtons you will get. Okay, yeah. Yeah, step by step is why I can solve this problem in 2 minutes also, but the thing is here what terminology you are supposed to consider. Understanding the problem is very important. Bhushan, hope you understand this question now. Okay, so what is the difference between the drawing and previous case? Drawing, in the drawing operation what happened? See, in the drawing operation we are applying load here, that is why we consider this cross section area. Now in case of extrusion process, then what happened? We are applying the force from the back side. We are applying the force from the back side. That is the reason why here I am going to apply pressure into initial cross section area, so that we are going to get the force required for the extrusion process. Hope you understand. Okay, right. Now so check your answer. So those people who solved along with me, check your answer and then we will move forward. Right. Right. Have a look on this next question, guys. Okay, welcome back. So now it is a question related to the forging. I have collected one drawing question, one extrusion question, which we have not, milta hai. No problem, Vishal. I'll send you. Okay. So once you contact within the Telegram group of our IMS GATE Academy, I'll upload that in that. Okay, no problem. But so better you carefully listen that along. Try to solve along with me. Okay, right. Right. Now let me read the question. It is related to the forging. An aluminium bloom with a diameter of 300 mm is forged using a closed die forging technique. Okay. So, and the initial height of the bloom was 60 mm and after forging it is reduced to 20 mm. The strength coefficient of aluminium is 760 megapascal and strain hardening exponent is 0.25. Determine the force required for the forging operation and consider coefficient of friction is 0.1. Consider the coefficient of friction is 0.1. Okay. Now let me so read the question and segregate the data. What is that? A forging is going to be happen. Which type of forging it is? It is a closed die forging operation. Closed die forging operation, in which what happen? A bloom of aluminium diameter, initial diameter is 300 mm, forged using the closed die forging system. Initial height of the bloom is 60 mm and after forging its height is 20 mm. Okay. Now the strength coefficient is 760 megapascal and strain hardening exponent is 0.25. Strength coefficient is, that is strength coefficient is 760 megapascal. Determine the force required for the forging operation. Okay. Now I just draw the briefly small diagram. Okay. Right. Now it is a initial height. So what is the initial diameter? Let me change my ink. Now initial diameter is 300 mm. So D naught I am taking initial diameter 300 mm. Okay. Now, so initial height is 60 mm. So this initial height is 60 mm. That is equal to H naught initial height. So this is going to be applied forging technique. So through forging operation, closed die forging, okay. Now what happened? The height is going to be reduced to 1 minute. I'll take right. So to the initial height of how much? To the initial height of final height of HF is equal to, it is 20 mm. Okay. Now we don't know that final diameter. We don't know that final diameter DF. Yes, guys. This is what happening in the closed die forging operation. Initial height to initial diameter is reduced to the height of 20 mm. Okay. So Bhushan, it is 277 meganewtons. No, Bhushan, it will come 246.27 10 to the power of 6 newtons. Okay, just follow that, so that we will go and just check my solution with your answer. Okay, right. Now this is what happening. So for that initial data is given, and strain hardening coefficient, and also strength coefficient and strain hardening exponent, and also mu is given. Okay. Now let us go for solve this question, and what we have to find? Force required for the forging operation. Okay. So for component is reduced from 60 mm height to 20 mm height, what is the force required? That is what we are supposed to find. Okay. Thank you all. Okay, right. Now let us go for solving the question. Force, drawing force, that means force required for the forging operation. Shall I go for the next slide, guys? Hope you understand the process. Now I'll tell you how to calculate the force required for this forging operation. Okay, right. Now, so force required for forging force is equal to F is equal to, I can write it is average flow stress into, it is AF, final cross section area, into, it is KS. Okay. So this is what the formula for calculating this one. Okay. Now here, what the things here? Here it is average flow stress, sigma average is average flow stress, average flow stress. Okay. So sigma average, I can write it as, is equal to, it is K into, epsilon F whole power n is divided by 1 plus n. Like that, you are supposed to calculate your sigma average. Okay. Now, so K is given now. So now let me write that strength coefficient. K is equal to strength coefficient. That is equal to, here how much they give? Strength coefficient, guys. Strength coefficient is 760 megapascal. Okay, right, 760 megapascal. All right. Next, epsilon F, that means true strain. That is equal to, it is ln of, HF is divided by H naught. HF is divided by H naught. Okay. Yes, guys. Right. Now here ln of your HF is how much, guys? HF is 20, H naught is 60. So now HF is 20 and H naught is 60. So that you are going to get minus, minus 1.098. 1.098. Why minus? Why minus? Because compression. Here the length is going to be reduced. That is why minus indicates that it is a compressive action. Compressive action. Isn't it, guys? It is a compressive action. Height is reduced in between the compressive force. So 60 mm height is compressed to 20 mm. That is why here true strain you are going to get it is a minus sign. Now you got EF and N is also given. Strength coefficient. How much given, guys? N? N is given 0.25. Strain hardening exponent is 0.25. Now here N equal to 0.25. Yes, guys. Now we found average flow stress. So if I substitute these values so that I can get average flow stress. Now we have to find AF, final cross section area of the component. So how can we find out the final cross section area of the component? So final cross section area of the component is equal to, it is pi by 4 df square, right? We don't know df. We don't know df, right? Now for that purpose, okay, now let us calculate that. So final cross section area AF is equal to, it is final cross section area. Final cross section area. Isn't it, guys? Okay. Now how can we write that? It is pi by 4 df square. But we don't know df, na? But we don't know df, na? How can we find df? Now in forging operation, in all metal forming process, either it is a rolling, drawing, extrusion or forging process, volume is constant. That means volume before forging equal to volume after forging. Now let us go for what is the volume over here. So volume of this component is equal to volume of this final component. How can we calculate the volume of this component? Area into height is the volume of the component. Area into volume of this component. So I can write it is, okay, I can write it is, so volume before forging equal to volume after forging. Yeah. Volume before forging is equal to volume after forging. Volume after forging. Volume before forging equal to volume before after forging. Yes, guys. Now from here, what is the volume? So pi by 4 d naught square into h naught is equal to pi by 4 df square into hf. Yes, isn't it? Volume is constant. Yeah, 246 meganewtons. Very good. Excellent, my boy. Excellent. Right. Now here, yeah, it is 246 meganewtons will come. Okay. Very good, Bhushan. Very good. Okay. Right. Now here, so pi by 4 will get cancelled. Now d naught square into h naught is equal to df square into hf. Okay. From there I require df. So now df is equal to, it is d naught into h naught by hf under root. Now d naught is 300 into h naught is 60, hf is 20 under root. Now from there you are going to get df is equal to 51.9. 519.16 mm you are going to get. Okay. Now from here you can get, so pi by 4 into df square. What is df? df is equal to 519.16 whole square. Right, guys? Now we find AF. So we got this, and now we have to go for this one. Strength coefficient. That means a friction factor, that is. Ks is a friction factor. Ks is equal to, it is a friction factor. Friction factor. That is equal to, I can write it is 1 plus, df into mu is divided by 3 into hf. Okay. It is mu, guys, coefficient of friction. It is coefficient of friction. It is coefficient of friction. Clear, everybody? Now we know that 1 plus, what is df? Just now we have found 51.916 into mu is, how much gave mu? Mu in the problem? Coefficient of friction. So 0.1, 0.1, right? Now let me write that 0.1 into 3 into 20. So that you are going to get Ks, friction factor. Yeah. Okay, okay, for sure, Sampath, for Sampath Kumar, very good. I'll upload, I'll send you the link. Okay, right. Now here, so I found that all three terminologies which are required for calculating the forging force. Sigma average flow stress I have found, and final cross section area I have found, and Ks also I have found. Now let me substitute all these values so that you are going to get your answer. Okay, right. Now let us go for this. Right. Forging force. Forging force F is equal to, it is sigma average. How can I write sigma average? K epsilon S power n is divided by 1 plus n into AF pi by 4 df square into Ks 1 plus, so df mu is divided by 3 HF. 3 HF. Okay. So now here K is 760 now. Now your EF is 1.098. Now your N 0.25. 0.25. Yes, let me check once. N is 0.25. Yeah, N is strain hardening exponent is 0.125. Right. Now let us go for is divided by 1 plus 0.25 plus pi by 4 into df square. What is df? 519.16 square into, you take it as a closed bracket, 1 plus df 519.16 into mu. So mu is how much, guys? Mu is 0.1. Mu is 0.1, right? Mu is 0.1 is divided by 3. Oh my God, what happened? Yeah, this is divided by 3. Oh my God, no. Here. Right, up to here only. 3 into HF is a 20. Now, if you solve this, you are going to get your answer is 246.27. 246.27 into 10 to the power of 6 newtons you will get. Okay. Yeah, Bhushan. So, hope you solved this. Yeah, it is 246 meganewtons also. Okay. Hope you understand, all of you, this question. But you should be very careful in remembering this formula, that forging force. Okay. Sometimes in the problem, do remember, guys, average flow stress directly they will give you. Average flow stress directly they will give you. Okay. But whenever they ask you to strain hardening exponent and also strength factor they gave, then in that case you are supposed to calculate your average flow stress by using this formula. Okay. So you should be mean value theorem, you are supposed to remember this one. Okay. In mathematics you will get mean value theorem na. So from there, here K into, you see, EF is a true strain, N is a strain hardening coefficient, it is a stress factor, now 1 plus N. So that average flow stress directly sometimes they give in the problem. Just question reading is most important thing, sir. Yeah, exactly, Bhushan, exactly. That is why once and twice, whenever you are going to solve the question, you just read the question once and twice. So with a fresh mind, so don't think anything else. Okay, if you read the question properly and write the given data, so that you will get in your mind all your preparation strategies and your preparation formula. Okay, that is what the thing here. Okay, now let us see that here sometimes they may give. So if they gave that AF and KS, if you remember, so that it will be easy to solve the problem. So hope you understand this problem, guys. Okay, so while you are substituting your true strain, don't keep negative. Okay, so negative sign is only for showing the direction. That means either it is a compression or it is a tensile. For showing that, we just use to minus, that is sign. Okay, now here it is showing minus, it is coming, means it is a compressive, right? That is the reason why you take only 1.08, 1.098 is the true strain. Clear, everybody? Hope you understand all. Okay, thank you very much. Right, now let us go for next question. Yeah, have a look on this question. I'll be back in a minute. Right, guys, welcome back. Welcome back the session. So here it is related to Bhushan daily 3-hour give production and industrial engineering, then possible out of mark this subject. Yeah, obviously 200%. If you spend more time, 3 hours time daily for production, so that you will be able to qualify for the gate. Along with that, you just prepare for the maths and also aptitude properly, and any other 2 related technical subject, it will be very easy to get the pass marks or qualifying mark in the gate. Okay, but you don't focus always qualifying marks. You target for 60 to 70 marks, so that you will be able to get 45 to 50 marks. Okay, that would be better. If you target for the less and target for the only qualifying mark, then it would be very difficult to get qualifying, Bhushan. Okay, so don't, first you remove your fear from the your mind. Okay, so focus on the things what you have learned. So you just okay, fine dear, no problem. Okay, thank you. Right, yeah, next is okay, right, now let me go for solving this question. Okay, that is a 2 mm thick metal sheet is to be bent at an angle of 1.6 radians with an radius of 150 mm. Distance of neutral axis from inside surface is 0.5 sheet thickness. Find the bending allowances. So here it is related to the bending allowances. Yeah, okay, no problem, Bhushan. Okay, so hope you helpful for this session also. Okay, thank you. Right, now here, okay, I don't think that you have finished your MTech. Okay, no problem. So you just follow these what to say, collected questions, so that it would be very helpful for you. Okay, right, now let me go for this. A 2 mm thick sheet, 2 mm thick metal sheet is to be bent at an angle of 1.6 radian, 1.6 radian. Now with a radius of 150 mm. Distance of neutral axis from inside surface is 0.5 mm to thickness. Okay, what we have to find? Bending allowances. Bending allowances. Okay, yeah, exactly. Yeah, so now I said that bending allowances. Okay, so bending allowances is equal to, I said that it is Rn into theta. Rn into theta. So now here Rn is equal to, what is that Rn? So Rn is the radius of the neutral axis. Okay, so from the bending center to the radius of neutral axis. Okay, now radius of neutral axis. Okay, now theta is the bend angle. Theta is a bend angle. Okay, right. Now Rn into theta. So now here theta is given now. Now let me go for the next slide. That is so bending allowances is equal to, it is Rn into theta. Now Rn I can write it is R into K into T into theta. Okay, where R is the bend radius. Bend radius. So where T is the thickness of the sheet. Where T is the thickness of sheet. All right. So thickness of the sheet is given in the problem now. How much, guys? 2 mm thickness. Okay, 2 mm thickness. Okay. Now, so K is the stretch factor. K is the stretch factor. Okay, so how can we decide stretch factor? Okay, now if let me solve this. If r is equal to, sorry, small r we have taken, na? Yeah, small r is greater than or equal to 2t, then your k will be 0.5. Yes, guys. Okay. Now, if r is less than 2t, then k is equal to 0.33. Okay. Now, let's check this condition. So, r is how much? R, bend radius. Bend radius given in the problem now. How much, guys? Bend radius. So, with a bend radius of 150 mm. Bend radius of 150 mm. Right. So, r equal to, it is 150 mm. Okay. And it is 2t, 2 into 2 is a 4. So, it is greater than. So, your k is equal to, for this question, is 0.5. Okay. Deciding the k is the key factor in this problem. What happened? If r is greater than 2t. So, what is r? 150. 2t is 2 into 2, 4. So, 150 always greater than 4. Na? That is the reason why your k will be for this problem is, 0.5. Okay. Now, let us calculate bending allowances. Okay. Let's calculate bending allowances. Now, bending allowances is equal to, it is going to be it is Rn, R plus Kt into theta. So, now here R is 150 plus K is, K we have to select 0.5. Why? Because R is greater than 2t. R is greater than 2t. Now, here it is 0.5 into 2 and into t. Theta is radians. Theta is given in the problem now. How much? Bend angle. Bend angle is given 1 point. How much, guys? Bend angle is 1.6 radians. 1.6 radians. Theta is equal to 1.6 radians. Okay, right. From here it is 1.6. Okay. If in the problem, if they mention bending angle in theta, you are supposed to, that is converted into radians. That is, you have to multiply with the pi by 180. But in this problem, they gave directly, theta is in radians. That is why no need to multiply with the pi by 180. So that if you solve this, then you are going to get your answer is, 241.6 mm you are going to get. Yes, guys. Hope you understand the problem. Right. So, bending angle. So, bending allowances can be used this formula. Now, let's go for next question. Yeah. Have a look on this question. Thank you, Bhushan. Thank you very much. So, I have collected, in a order way. So, first is what is that rolling, and then drawing, and then extrusion, forging, and bending, and then here this formula for punching and blanking operation, sheet metal operation. Okay. Thank you very much for your compliment. Okay. Now, let us go for have a look on this question. Okay. Right. Now, see, the ratio of press force required to punch a square hole 30 mm side in a 1 mm thick aluminium sheet to the ratio, to that need to punch a square hole of 60 mm side in a 2 mm thickness aluminium. Okay. So, what they ask you to calculate. So, first understanding the problem is very important, guys. What is that? The ratio of press force required to punch a square hole 30 mm side in a 1 mm thickness aluminium sheet, to that need to punch a square hole of 60 mm side in a 2 mm thickness of plate. Okay. Understanding the problem is, no Banerjee, it is not exactly. No, wrong answer. Check your answer once. Check your answer once. Okay. Yeah, 0.25 is the correct answer. Very good. Very good. Now, let me solve this. Now, the ratio of press force to punch a square hole of 30 mm side. First, we will calculate the force required for punch a 30 mm square hole. Okay. Now, force required for punch a square hole. Okay. Force required for punching. Force required for punching. Force required for punching. So, can we say it is F1? Why? Because for 30 mm side we are calculating. For 30 mm side we are calculating. So, F1 is equal to, here what is that? Force required for that, shear stress into shear area is the force. Okay, force required this. Now, next is what is shear stress is remains same, and what is shear area? Perimeter into thickness. Perimeter into thickness. So, now shear stress into perimeter. So, what is a perimeter? It is a square hole. Square hole perimeter is 4A, na? So, 4A. Okay, 4 into A. Side is A. And T is how much for first thickness in a 1 mm thickness plate? So, that is T is 1 mm. Such that I can write it is TS into 4 into 30 mm side square hole into 1. So, we will keep like that only. Okay. Next what that? To this punch force ratio, to that need to punch a square hole of 60 mm in a 2 mm thickness sheet. Okay. Force required for punching. Next. Force required for punching. Force required for punching. Force required for punching. Say we say F2, that is equal to shear stress into shear area. Now shear stress I'll keep like that only, same material na. Now perimeter into thickness. Okay. Now what is the perimeter here? Here also 4A into thickness is 2 mm here. Okay. Now here side is here. How much, guys? 60. 60 only, no? Let me go back. Right. So square hole of side 60 mm. Isn't it, guys? Right. Now 60 mm into 2. Such that, so this is your F2. We'll keep like that only. Okay. So tau S into 4 into 60 into 2. Okay. Now what they ask you actually in the problem. Okay. Yeah, I will send you. I'll send you. Okay. Right. Now let us, what they ask you in the problem, F1 by F2 they ask you to calculate. For that, sigma S into, it is 4 into 30 into 1 is divided by tau S into 4 into 60 into 2. Okay. Now 4 will get cancelled. Right. So now this fellow will get cancelled, and 4 will get cancelled. So here it will go for 30 by 120. So that it is gonna be a 1 by 4. So that your answer is 0.25. Okay. Now your F1 by your ratio of punch force required to square hole 30 mm to 60 mm is 0.25. Right. Okay, I'll send you Navneet, no problem. Right. Now this is what how to solve the problem. Hope you understand the problem, guys. Okay. Right. Next question. I just shifted our talk onto. So far I have covered that metal forming process, guys. Now I just shift my talk onto metal cutting operations. Before that, I'll take a 2 minutes break, and you will be here only. Be in touch. So we will solve. So break for 5 minutes. Yeah, thank you all. Welcome back, students. Thank you for the patient lesson. Okay, right now. So let us go for next question. Right. See this question, I just shift my talk onto metal cutting, and very important chapter, metal cutting operations. Okay, in this definitely there is a 2 marks question. Sometimes it is possible linked answer question may come for 4 marks. Okay, very important concept and very important chapter for GATE aspirants. Okay, now let us have a look on the question. Okay, what is given in the question, and let me solve the question. Okay, first I'll read the question, have a look on that, guys. Right. Now, in an orthogonal cutting operation, the following data have been observed. Okay, in an orthogonal cutting operation, the following data have been observed. That, right, first one is uncut chip thickness, T1 is given 0.127 mm, and B, width of the cut is 6.35 mm, and cutting velocity or cutting speed is given 2 meters per second, rake angle is given 10 degrees, and cutting force is 567 newtons, and thrust force is 227 newtons, and T2 uncut chip thickness, not uncut, cut chip thickness is 0.228 mm. So what we have to find? Okay, right, determine shear angle, friction angle, stress along the shear plane, that means shear stress we have to find. Okay, so first this one, shear angle, second is friction angle, third is shear stress we have to find. Next is power for the cutting operation, that is a fourth one. Okay, now what we have to find? Find the chip velocity is a fifth parameter. Okay, now next is shear in chip and shear strain rate. Okay, shear strain rate and also shear strain we have to find. Okay, shear strain and shear strain rate we have to find, that is total 6 and 7. Okay, here it is a lengthy question. Actually, this much length of the question will not ask, any 2 parameters will ask, but for practice purpose I have collected these questions. We have solved all these ones so that it will be possible to get some confidence on the metal cutting. Clear, everybody? Okay, so this is what the given. First, shear angle. So what is shear angle? So shear angle, first we'll calculate shear angle. Right, next shear angle is equal to excuse me, shear angle we indicate with a phi. Okay, now shear angle is equal to, it is tan phi is equal to r cos alpha is divided by r sin alpha, or 1 minus r sin alpha, 1 minus r sin alpha. Okay, guys. Okay, now what is r? So we know that r equal to, it is uncut chip thickness by chip thickness, that is T1 by T2. So what is T1? T1 is 0.127, T2 is 0.228. Okay, right, 0.127 is divided by 0.228, so that you are going to get your r is equal to, 0.557 you will get. So alpha is given in the problem, na? Shear angle is, rake angle is 10 degrees, right? So rake angle is 10 degrees, alpha is given 10 degrees. Yes, guys, right. Now let us, oh my god, right, now substitute that. So tan phi, na? So I require phi. Okay, for that purpose I'll take, so directly phi equal to, it is tan inverse of r. R is 0.557 into cos 10 degrees divided by 1 minus 0.557 into sin 10 degrees. Okay, if you solve that, your shear plane angle is equal to, you are going to get it is 31.25 degrees will come. This is what your first solution, shear plane angle can be calculated. Okay, yeah, Bhushan, it is 31 degrees and beta is 32 will come, and so okay, let me solve myself. Okay, later we can go check your answer. Okay, so first I have found that capture question first. Actually, shear plane angle, friction angle, shear stress along the shear plane, power in the cutting operation, find the chip velocity, shear stress in the chip, shear strain rate also. Okay, right, 7 parameters I gave. Okay, right. Next is beta, friction angle. So friction angle we indicate with beta, right? So now we have a relation that from the merchant circle tan inverse, oh my god, no, not tan inverse, right? So tan of beta minus alpha is equal to, it is Ft by Fc. Do you remember this relation? Thrust force is divided by cutting force. From there I require beta na, so I can write beta is equal to, it is, you know, alpha plus tan inverse of, you know, Ft by Fc. Okay, now alpha given, Ft and Fc also given, right? So now what is that? Cutting force 227, cutting force 567, thrust force is 227, right? Now from there I just substitute the values. Okay, it is gonna be a 10 degrees plus tan inverse of, you know, 227 is divided by 567 is a cutting force, such that I am going to get my beta is equal to, it is 32.62 degrees. 32.62 degrees I am going to get. Okay, right. Yeah, thank you, Praveen Kumar. Thank you very much. Right. Now beta we got. So in future we require mu also na. That is why coefficient of friction also we find that. What is that? Tan beta is equal to, it is mu, right? Beta we know na. So now beta we know. So mu equal to tan of, so 32.62. 32.62. Now mu equal to, you are going to get mu is 0.64. All right, guys. So 0.64. Shear stress you are going to get 236.5 here. 236.5. Okay. Yeah, check your answer with me. Right. Next is let us go for shear stress. Shear stress only na. Right. Shear stress only na. What is that? Next one we have to calculate. Yeah, shear stress along the shear plane. Right. Shear stress along the shear plane. We have a relation for shear stress. We have a relation for shear stress. Okay. That is equal to third question na. Third question. Shear stress. Shear stress is equal to, okay, tau is equal to, it is shear force into sin phi is divided by T1 into B. Yes. Yes, guys. But we don't know that Fs. Shear force we don't know, right? Only cutting force and thrust force we know in the problem. So only cutting force and thrust force we know in the problem. So cutting force only, thrust force only given. But we don't know that, what is that? Cutting for shear force. For that, first we have to calculate shear force. We know that shear plane angle, uncut chip thickness, width of the cut is also given, right? First find out the Fs. Okay. From the merchant circle, we have a relation between the cutting force and also thrust force, isn't it, guys? Right. Now from merchant circle, from merchant circle, I'm sorry. From merchant's circle, we have a relation. What is that relation? Cutting force is divided by cos of beta minus alpha. Yes, cos of beta minus alpha is equal to Fs shear force is divided by cos of, you know, beta minus alpha plus phi. This relation we have. We know that cutting force, we know friction angle, rake angle, shear plane angle we know. So if you know all these angles and one force if you know, so that it is possible to find out the shear force. Now let us calculate the shear force, guys. Shear force is equal to, here Fc into cos of beta minus alpha plus phi is divided by, you know, cos of beta minus alpha. Clear, everybody? Hope you understand this. Okay. Now let us substitute the values, Fc value and beta value, alpha value, phi value, and if you substitute that, so that you are going to get your shear force. Okay. Now shear force is equal to, right, shear force is equal to Fc. Fc is how much? 567 na? 567 into cos of beta. How much we got beta? Beta we got 32.62. 32.62. right? 32.62. Oh my God, oh my God. 32.62 minus 10 is a rectangle plus 5 is how much we got 5? 31.25. 31.25. So is divided by cos of beta minus alpha, that is 32.62 minus 10 degrees. So that you are going to get your shear force is equal to how much, guys? Shear force, you are going to get 367 newtons. 367 newtons you are getting shear force. Okay, right, everybody? So are you following, guys? Yeah. Now shear force we got. Now shear stress. Shear stress is equal to tau is equal to, it is a shear force into sine phi is divided by T1 into B. Yes, guys. Now shear force 367 newtons into sine of phi is how much, guys? 31.25 is divided by T1. So 0.127, I guess. Let me check that. Yeah, 0.127, and B is how much we got B? B is 6.35. 6.35 width of the cut. B is given in the problem now. Yeah, B width of the cut is 6.35. Now from there, if I solve this, so I'm going to get my shear stress is equal to, it is 236. Oh my God. 236.25 Newton per mm square. This is what you are going to get your shear stress. Okay, check it once, your shear stress. Okay, next is power. Power we have to calculate. Right, power we have to calculate. 236.5 Newton per mm square will come. Okay, right. Next is here we got that third question. Now let us go for fourth question. What is the fourth one? We have to find power. Power required for cutting. So that is P equal to, it is cutting force into cutting velocity. Sorry, cutting velocity or cutting speed. Okay, right. From here, FC is equal to 567 into cutting speed. What is cutting speed given in the problem? Cutting speed is given, 2 meters per second. 2 meters per second. It is 2 meters per second. Okay. So now Newton meter per second. So Newton meter is joule, joule per second will come. So now I just required in kilojoules, the kilojoules or watts. Newton meter is a joule, joule per second is a watt. So kilowatts I require. So that I just divide this into 1000. So that I'll get 1.134 kilowatt power I'll require for this operation. Clear, everybody? Okay. So kilowatts I found. Newton meter is a joule. Joule per second is a watt. So you'll get watts. So by 1000 kilowatts I'll get the answer. Clear, everybody? Right. Next is chip flow velocity we have to find. Okay. Chip flow velocity. Chip flow velocity. Chip flow velocity. That is chip flow velocity. We know the formula that chip flow velocity is a VF. Okay. Now we have a relation that VF by VC is equal to R. VF by VC equal to R. Now we know VC and VF we have to find. VF is equal to, it is R into VC. Now VC is 2 meter per second and this is 0. R is equal to how much? It is 0.557. 557 into 2 meter per second. So your VF is going to become 1.114 meter per second will come. Okay. So remembering the relation is very important in the metal cutting. Okay. So from the merchant circle we have derived that so many relations. Okay. In that power relation, right? Now this is one more relation, right? Now here if you go back, this relation is also very important. Yes, guys. Okay. Now this shear stress also like that. So if you find if you able to remember this relation, so that this relation also This relation tan beta, oh my god. Yeah, this relation also, right? Remembering relation is the key of the solving the questions, right guys? Okay, from there, so just now go for that. Next shear stress we found, shear flow velocity we found, velocity we know that. Next is what we have to find, I guess shear strain we have to find, right? Shear strain. Yeah, shear strain rate we have to find, guys. Shear strain is equal to SS we call, it is cot phi plus tan phi minus alpha. Cot phi plus tan phi minus alpha is your shear strain. Now cot phi. So cot of phi is, I guess, 31.25 plus tan of, okay, 31.25 minus alpha is 10 degrees. Okay, from there I can get my shear strain is 2.037. 2.037 is my shear strain. Clear everybody, guys? Okay, right. Now let us go for shear strain rate. This is what your, how many, question number 6. Question number 6. Next is shear strain rate. Shear strain rate. Shear strain rate. So shear strain rate is equal to, you know, shear velocity is divided by shear plane length. Shear velocity is divided by shear plane length. Okay, right. Shear velocity is divided by, okay, shear plane length. Shear plane length. Right. Now here let me draw the small diagram to show these two fellows. Okay, right. Right. Now here where is shear is going to be happen? Right. This is a shear plane. Okay. Whatever the, so here this is your shear plane. Right. Shear is going to be takes place or here. So what is the shear plane length? So shear plane length is this. So here I am taking it as a L0. So L0 is a shear plane length. Now shear flow velocity. How the shear flow velocity is going to be for? Shear flow velocity will takes place along this direction. Vs, shear velocity Vs. Okay. Now shear velocity divided by shear plane length, so that you are going to get shear strain rate, guys. Clear everybody? Okay. So hope you understand. Now let us calculate that Vs and also L0. So for calculating L0, this is what? Phi, shear plane angle, and this is what? T1. Okay. Now I require this one. Okay. For that let me draw this. So if I take it is a triangle A, and this point is B, and this point is C. So from triangle ABC is equal to, it is sin phi is equal to, how can I write my sin phi? T1 is divided by L0. So L0 is this also L0, na? Right. T1 divided by L0. T1 is divided by L0. So it is not H. T1 is divided by L0. I require L0. So L0 equal to, here it is, you know, T1 by sin phi. So that you are going to get your L0. Clear everybody, guys? Okay. Now shear plane length we got. Now we have to find shear flow velocity. So shear flow velocity is, now shear flow velocity is Vs is divided by shear plane length is L0. If you do that, so that you are going to get your shear strain rate. Hope you understand, guys. Okay. Now let us go for that. Calculate that Vs. Now we have a relation that velocity triangle. Do you remember velocity triangle in the much in the metal cutting. So velocity triangle. So from the velocity triangle, I'll get the relation that shear flow velocity is divided by cutting speed is equal to, I'll get it is cos alpha is divided by cos of phi minus alpha, right? So from there I can find this one. Okay, now Vs is equal to shear velocity, that is equal to Vc into cos alpha is divided by cos of phi minus alpha, isn't it? So now here Vc is 2 into cos 10 degrees is divided by cos 31.5 is how much? 31.25. 31.25 minus 10 degrees, okay, such that I am going to get my Vs is equal to here 2.1 mm per meter per second, because so I have considered it as a meter per second, that is why Vs also comes for meter per second. Similarly, you find that what is that? Shear plane length. So length of shear plane is equal to, it is T1 by sin phi. So what is T1? T1 is 0.127 and sine of 31.25. Okay. So from there you will get a shear plane length is equal to 0.245. 0.245 mm. Okay. Right, guys. So hope you understand all. Okay. Right. From here, so we got Vs, we got L0. So now our shear strain rate is equal to Vs by L0, right? Now here let's go for calculate that shear strain rate is equal to, it is Vs is divided by so L0. Okay, now Vs is how much? Vs how much, guys? 2.11 meter per second is divided by, units are very important, guys, units are very important. Okay, now it is 0.245 mm, 0.245 mm, 0.245 mm. Okay, now I just convert my equation into, so here it is in meters, here it is in mm, right? Now from there I'll write it is 2.11 into 10 cube mm per second, right, is divided by 0.245 mm. Okay, so now mm will get cancelled, guys, mm will get cancelled, and second 1 by second you will get, so that you are going to get here answer is shear plane rate 86.12 into 10 to the power of cube 1 by second, so that I can write it is a second inverse. Clear, everybody? So like that you are supposed to calculate your parameters. So if you want to solve these kind of questions related to the metal cutting, you should be very aware about the merchant circle and also velocity triangle and relations which we have established through the metal cutting, merchant circle. That also very important in solving this kind of questions. Okay, however, it is a lengthy question, but this kind of question will not ask in GATE. But the thing is here, I collected this question for practice of all the parameters which are related to the metal cutting. We have covered almost all things in this question. So if you look at that, see here in the question, see shear angle, friction angle, and shear stress, and also power, and also find the chip flow velocity and shear strain in chip and shear strain rate also. Shear strain rate is nothing but shear velocity is divided by shear plane length is the shear velocity. Clear, everybody? Okay, shear strain rate. Now let us go for, I hope you understand this solution. Now let us go for another question. Yeah, have a look on this question, guys. Right, not this question. Yeah, have a look on this question, guys. A diameter of, we'll go for the previous question only. Yeah, so have a look on this question, then we will forward. Next question we will solve that. Right, now have a look on this question. So for orthogonal cutting operation, for orthogonal cutting operation. So uncut chip thickness T1 is given. Now let us go for pen. Now for orthogonal cutting operation, uncut chip thickness is given, cutting speed is given, rake angle is given, width of cut is given, chip thickness is given, and also cutting force is given and thrust force is given. What we have to calculate? What we are supposed to calculate? That calculate the percentage of total energy that goes into overcoming the friction at chip tool interface. Okay. So what is the energy is going to be consumed? Suppose if you take the total energy during the machining operation, total power, how much power required for overcoming the friction? That is what we are supposed to calculate in this one. Okay. Suppose say that 100 kilowatts, suppose say that 70 kilowatts are going to be used for the metal cutting operation. In that 70 kilowatts, how much amount of the power is required for overcoming the friction? How much percentage of power required for overcoming the friction we are supposed to calculate? Clear everybody? So now let us go for calculate, how to calculate this one. Okay, right. Now what is that? What they ask you to calculate? Calculate the percentage of total energy that goes into overcoming the friction at chip tool interface. Okay. Now, so percentage of power or energy required to overcome friction. Yes guys, overcome friction, right? Now what is the total energy? What is the this one? So now let us write the formula so that you will be able to understand that. Right. Now from here, so total energy, so friction energy required for overcoming the friction, that is friction energy is divided by, so total energy. Now how do we calculate friction energy? Friction force into chip flow velocity is divided by cutting force into cutting velocity is the total power. So this is into 100, so that you are going to get your percentage of frictional force required to overcome the friction. Clear everybody? So friction force into velocity of chip flow velocity in the friction zone, and total energy is equal to Fc into Vc. So that if I take that percentage, so that I can get the power required to overcome the friction. Clear everybody guys? Okay. Now let us solve that. So we know that Vf by Vc equal to 1. We know that Vf by Vc equal to R. Okay. Now I just rectify my formula that so that is equal to, I can write it is, so F by Fc and Vf by Vc into R na, so that is equal to R into 100. Yes guys, F by Fc into R. Clear everybody? So now let us calculate. Fc is given, F we have to find, and also R we have to find. So now let us go to calculate that R. So R equal to, what is that R? Now R equal to, it is T1 by T2. So what is T1? So let us go back to our data. T1 is 0.127, T2 is 0.229. 0.127 is divided by 0.229. That is equal to, R equal to, you are going to get, it is 0.55 you are going to get. Okay. Friction energy divided by total energy. So for that, first I have calculated R. Now we have to focus on F. We don't know F now, right? So we don't know F. That is the reason why here we have to find F. Okay. Now let us go how to find the F. Frictional force. Frictional force F is equal to, from merchant circle, I can write it is R into sine beta. R into sine beta. Yes, guys, R into sine beta. So, as we know that F by R, meanwhile, I'll just write this. So, I'll write full formation. Frictional force F from merchant circle, okay. From there, I can write R is equal to, F equal to, sine beta by R. F equal to sine beta equal, not exactly. F by R equal to sine beta, I'm sorry. F by R equal to sine beta. F by R is equal to sine beta from merchant circle. Now I required F, that is why R into sine beta. So where beta is a friction angle, okay. No, not Bushen, not 60%, not 60%. Right. Now R into sine beta. Now what is R? R equal to, it is, I can write it is from merchant circle itself, FC square plus FT square under root. Okay. From there, I can write my FT square is equal to 556 point. Now what is given? Friction cutting force 556.25 is this one. Yeah, 556.25 square plus, it is 222.50 square under root. Okay. If I am able to solve this, so that I am going to get, it is 600.72 newtons, I am going to get R. Okay. Now I don't know the beta. I don't know the beta friction angle. Now I am supposed to find out the beta as well. Okay. So for that purpose, again I am going for the relation, next slide. Tan of beta minus alpha is equal to, it is Ft by Fc. So from there I can write my beta is equal to, it is alpha plus tan inverse of Ft is divided by Fc. Okay, right. Alpha is 10 degrees, I guess, plus tan inverse of 222.50 is divided by 562 point how much Fc, 556.25. 556.25. 556.25. Okay. Now if I solve that, so that I am going to get my beta is equal to 32 degrees. Okay. Now for calculating the F, I require R. R I found. B, beta friction angle I found, that is 32 degrees. Now let us calculate that F. So F is equal to, it is R into sine beta. Okay, right. R is equal to 600.72 newtons into sine of beta is 32 degrees. Okay. From there, I can get my frictional force. How much? Frictional force I am going to get, it is 318.34. 318.34 newtons I am going to get my frictional force. Clear everybody, guys? Okay. So hope you understand all. Right. Now from here it is F equal to 318.34. Okay. Now so let us go back. So R we know and F we know, Fc we know, and substitute in that. Okay. So now friction energy divided by total energy is equal to friction energy is divided by total energy is equal to, it is how much, guys? F is divided by Fc into R. F is how much? F 318.34 into R is 0.55. Okay, and divided by 560. What is that? 556.25 into 100. So that you are going to get it is approximately 31.75. Right? Check your answer, Bhushan. Yeah. Finished now? So now hope you understand the question. So like that you are supposed to calculate. Okay. Now let us go for next question. Right. Have a look on this question, guys. Have a look on this question. Right. So have a look on this question. I'll be back in a minute. Yeah. Welcome back. Let me read the question once, guys. Right. A Taylor's two-life equation for a machining C40 steel. So here it is not C value, it is a type of steel, guys. Okay, the Taylor's two-life equation for machining C40 steel with a 18:4:1 HSS cutting tool at a feed rate of 0.2 mm per minute, and the depth of cut is 2 mm is given by Vt power n equal to C, where n and C are the constant, the following Vt values. Okay, so V is going to be vary like this. Suppose cutting speed is 25 meters per minute, then the tool life is 90 minutes. Then the tool life is 90 minutes. Now, if the cutting speed is increased to 35, then the tool life is reduced to 20 minutes, guys. Okay. Now, what we have to find here? Okay. Now, here we have to find here N and C values, N value and C value. Next, second question. Hence, recommended the cutting speed for the desired tool life of 60 minutes. Okay. If the tool life is 60 minutes, what will be the cutting speed? You are supposed to find out. Okay. Now, so let us go for here, guys. Okay. Suppose here, if I take that it is a V1 and this will become T1. If I take it is V2, this become T2. Yes, guys. So, for cutting speed 25 meters per minute, then the tool life is 35. No, oh my God, 1 minute, little bit confusion. Right. Now, if my cutting speed is V1 25 meters per minute, then my tool life is T1 90 minutes. If my cutting speed is V2, 35 meters per minute, then my tool life is going to be 20 minutes. Isn't it, guys? Okay. Now, I have to find N and also C. Okay. So, I gave you one direct formula and derivation for this also, that is N equal to, how can I get N equal to? It is log, so V2 by V1 is divided by log, T1 by T2. Log V2 by V1 is equal to log T1 by T2. So, as we know that what is V2? V2 V1. So, V2 is 35, V1 is 25, right? So, V2 is log 35 is divided by 25 is divided by log, T1 by T2. What is T1, T2? T1 is 90, T2 is 20. Okay. So, now here it is 90 by 20. Now, if you solve this, your N is equal to, you are going to get it is a 0.225, right? 0.225 you are going to get. Now, here what happened? So, first we have to calculate that N. Now, let us go for C. Now, V1 T1 power N equal to C. Okay. Now let us calculate that. What is that V1? V1. So V1 is 25, T1 is 90. V1 is 25, T1 is 90. Right. Now V1 is 25 and T1 is 90, whole power 0.225 is equal to C. Right. Now if you calculate that, C you are going to get, it is C you are going to get 68.8. 68.8 you are going to get as a C. Now this is what the first question is finished. First question is finished. Okay. Now what is the next question? They ask, hence recommended the cutting speed for a desired tool life of 60 minutes. Recommended the cutting speed for the desired tool life of 60 minutes. Okay. So what cutting speed is required for the tool life of 60 mm? Okay. Now let me write that. Right. Now, so recommended cutting speed for 60 minutes of tool life. 60 minutes of tool life. 60 minutes of tool life. All right. Now for that, so here V into, so T is 60 minutes and 0.225 is equal to 68.8. So N and C are constant. From there you calculate that V. So V is equal to, it is 68.8 is divided by 60 power 0.225. Now your V is equal to how much you are going to get? 27.39 meters per minute you are going to get. So like that you are supposed to solve your question. Yes guys, hope you understand the question and solution as well. Right. Next is another question. Yeah. Have a look on this question. I'll be back in a minute. Yeah, welcome back guys. Let's have a look on this question. That is bar of 250 mm length and 25 mm diameter are to be turned on a lathe with a feed rate of 0.2 mm per revolution. Okay. And each regrinding of the tool cost is 20 rupees and the time required to tool change is 1 minute. Okay. Right. Next up, tool life equation is given by Vt power n equal to 0.2 equal to 24, where V is the cutting speed in meters per minute and tool life is T in minutes. Optimum tool cost per price for maximum production rate is, okay. So optimum tool cost per price for maximum production rate is Rs rupees of something. Okay. We have to find that. Now let me segregate the data what is given in the problem. Okay. Right. A bar of length. So this much length of the workpiece and this is the diameter of the workpiece are to be turned on a lathe. So turning operation has been performed on a lathe. Okay. Now at a feed rate of 0.2 mm per revolution, each regrinding tool cost is 20 rupees. Okay. So for every time if you go for grinding of the tool, that takes 20 rupees of cost. Okay. Next, the time required for each tool is 1 minute. Okay. So tool changing time is equal to 1 minute. Tool life equation given as Vt power n equal to 24. Okay. Where n is a 0.2. Now V is the cutting speed, optimum tool cost per price, maximum production rate. Now let me write the given data. Okay. Now length of workpiece. Length of workpiece, that is L equal to how much guys? It is 250 mm. Length of workpiece is equal to 250 mm. Next, diameter of the workpiece. dia of workpiece, that is D is equal to, it is 25 mm. Okay. Now it is turned on a lathe. Now feed rate is equal to, feed F is equal to, it is 0.2 mm per revolution. 0.2 mm per revolution. Yes, guys. Next, tool change time. No. So each regrinding cost, tool regrinding cost. Tool regrinding cost. Tool regrinding cost. Tool regrinding cost is equal to 20 rupees. Okay, right. Now tool change time is 1 minute. Tool change time is equal to 1 minute. Okay, right. Next is, Vt power n equal to, Vt power 0.2 is equal to 24 is given. Yes, guys. Now we have to find optimum tool cost for price for maximum production rate. So here, based on that, you are supposed to calculate that. What is that? It is a maximum production criteria. We have a 3 criteria now: minimum cost criteria, maximum production criteria, and maximum profit criteria. 3 criteria we have. Okay. In those 3 criteria, it is a maximum production criteria. Okay. Right. Now for that, maximum production criteria. Maximum production criteria. Okay. So for maximum production criteria, what is the optimum velocity? V optimum is equal to, it is C into, it is C into N by 1 minus N, okay, minus 1. Sorry, no, not minus 1. Right. And it is 1 by Tc into 1 by Tc whole power n. Okay. Now let us calculate that. C is how much? C is given in the problem now. C is equal to 24. N equal to 0.2. Right. Now C is equal to 24 and N is equal to 0.2 is divided by 1 minus 0.1 minus 0.2 into 1 by 1 whole power 0.2. Okay. So from there I can get it is V optimum, I am going to get it is 18.18 meters per minute. Now similarly T optimum. T optimum is equal to, that means optimum tool life. Optimum tool life is equal to, it is 1 minus N is divided by N into tool change time. Okay. Now that is gonna be a 1 minus 0.2 is divided by 0.2 into 1. Okay. Tool change time is 1 only, na? Yeah, 1 only. Now from here I am going to get optimum tool life is 4 minutes. Optimum tool life is 4 minutes. Okay, right. Next is what we have to find. Next is time for turning operation. Time for, we got tool life. Next, time for turning operation. Time for turning operation. Time for turning operation. So that is equal to, we know that it is a L by F into N, where L is the length of the job. Okay. Now N we have to find. So now N equal to, it is 1000 V is divided by pi D. Okay. Now 1000 into, so 18.18 is divided by pi into D. How much D it is? So D is, have a look on that D. What is the diameter of the workpiece? 25. 25 is a workpiece diameter. Now you are going to get your N is equal to 231.4. 231.4 RPM you will get. So now we know that L is 250 is divided by F is how much, guys? F given in the problem, feed rate is 0.2 mm per revolution. 0.2 mm per revolution into 231.4 rpm, such that your machining time is going to be, you are going to get machining time 5.397 minutes. 5.397 minutes you are going to get. So now you got machining time. You got machining time. Now you got tool life. Okay. Now let us go for number of tools required for turning. Number of tools required for turning. Number of tools required for turning. That is equal to, so machining time divided by tool life. Machining time is divided by tool life. Machining time is divided by tool life. So what is machining time? 5.397 and tool life is equal to, tool life we have found now, optimum tool life is 4 minutes. Optimum tool life is 4 minutes. Now, so that you are going to get here number of tools required for machining 1.349. 1.349 number of tools required for machining operation, right? Now, what they ask you to calculate optimum tool cost. Okay. So now optimum tool cost for price. Optimum tool cost for price, tool cost price is equal to, it is going to be a number of tools for turning, number of tools for turning operation. Okay, this is multiply, so cost for regrinding tool, cost for regrinding each tool, regrinding each tool. Okay, now number of tools required is, just now we have find now 1.349. 1.349. This is into cost of each regrinding tool. Cost of regrinding each tool. So what is cost of regrinding each tool? 20 rupees. Now this multiply with a 20, so that you are going to get, it is 26.98 rupees. Right, like that you are supposed to calculate this particular question. Okay, so understand the question is important, guys. Okay, now let us go back to the question. So here turning operation has been performed on a 250 mm length and 25 mm diameter one. Now with the feed rate of this much. So for regrinding of every time for the tool is 20 rupees. Now tool change time is 1 minute. Now I just calculate for doing this operation how many number of tools required and what is the tools tool life. Okay. Now for that total machining time divided by tool life, so that I will get my total number of tools required. So total number of tools required into cost for each tool for regrinding, so that I will get optimum tool cost for the operation. Clear, everybody? Hope you understand. Right, now that's all for today's session. Okay, now let us go for new batch announcement. New batch announcement, guys. Right, live online new batch for GATE 24-25. Date is Tuesday, January 3rd, 2023, and ECE, EEE and instrumentation, signals and systems. Signals and systems for mechanical engineering mechanics for CS TOC will start for online batch, and second batch will be Saturday, January 2023, and ECE, EEE instrumentation networks will start. And for mechanical and civil, it is for mechanical and hydraulics, and CS for operating system. So for joining online batch, live batch, so for GATE point of view, you just contact these two numbers. Alright, guys. Next, for classroom new batch offline. Okay, now that will be start on January 8th, so 2023. For ECE, EEE instrumentation digital will start, mechanical and civil strength of material will start offline batch, guys. Okay, now CS is a digital. Now our office is for contacting the offline classes, Jayanagar, Gate, IMS Gate Academy, 41, 4th floor, South End Road, Basavannagudi, Bangalore. Landmark is above Adishwar Supermarket, 560040. For contacting through telephone, then you may use this. Okay, you may contact through the WhatsApp also. This is for offline batch. So previously we have discussed that online batch. Next is hybrid classroom. Hybrid classroom means it is a combination of online and offline. Okay, 70% is a offline, 30% is a online, is a hybrid classroom. Now hybrid classroom batch will start Tuesday, January 3rd in signals and systems for ECE, EEE and instrumentation. Next, mechanical and civil engineering mechanics. Okay, next Saturday, January 8th. So another new batch that is going to be control systems for ECE, EEE and instrumentation, and mechanical and civil is a FM and hydraulics. Address is 40-1-59, 3rd floor, BOI building opposite Modern Supermarket, Ben Circle, Vijayawada. So hybrid classrooms will be conducted in Vijayawada. Those people from Andhra Pradesh, you may just contact with these two numbers so that you will be enrolled for the IMS GATE Academy for the hybrid classroom classes. So in hybrid classroom, we have a 70% of offline classes, 30% of online classes, guys. Okay. Now I hope you enjoyed the session. Now I have covered here metal forming process and also metal cutting. In metal forming process, I have covered the wire drying operation, extrusion process, and also forging operation, bending and sheet metal operations I have covered. And in metal cutting, if you come under metal cutting I have been covered that metal cutting, how to solve the forces and power calculations and other parameters in the metal cutting. And apart from that, I have solved that tool life equation, and also one more thing, we have economics of machine cutting, machine tools. Economics of machining also have been solved. So I hope you enjoy the session. Tomorrow we are going to cover that machine tool operations and advanced machining process, such as non-traditional machining process, CNC, metrology and material science questions are going to be solved tomorrow session. Okay. Thank you all. Thank you for the patient listen. Thank you all.